Heart attacks come about when blood vessels in the heart are blocked. And without a supply of oxygen-rich blood, the heart muscle can die. This is called ischemic injury and can also occur in other places in the body, leading potentially to tissue death and even limb amputation. But what if it was possible to rebuild the blood vessels in the heart or in other areas of the body to kickstart the circulation and prevent tissues from being starved of oxygen and dying? This is what Jo Mountford is trying to do at the Scottish National Blood Transfusion Service, and she explained her work to me, Katie Haler.
We're talking about endothelial cells, and endothelial cells are the cells that line blood vessels and are the major component of blood vessels. So, for example, if you have a heart attack, the blood vessels become occluded and you lose blood supply to that tissue. And once that tissue is lost, then you can't rebuild it. So you have to put the blood vessels back in first before you can start to rebuild the tissue. We're doing this not using the patient's own cells, but using cells called pluripotent stem cells, which are essentially cells that we can grow in the laboratory for indefinite periods, and they'll also stay in their immature form, and then we can turn them specifically into the tissue that we want, because these pluripotent cells have that capacity to make anything, and then hopefully transplant it back into the patient where it will form the tissue that we desire to rebuild.
Wow, that sounds really cool. It also sounds fraught with potential complications. How easy is this to do?
It's really challenging. So the key thing with these cells, because they can make anything, they want to make everything. So they try and differentiate or mature into all different things at the same time. So the key skill is taming them to become exactly what you want them to be and not what they want to be. And to do it on a timescale that's also compatible with treating patients and in numbers large enough to treat them. So we need many billions of cells, for example, to treat patients, really large-scale production. And additionally, if we're talking about doing this for clinical use, everything has to be done at a really, really high quality. So using reagents that have been tested and using protocols that are really, really, really reliable, so we get the same thing time after time after time. And it's that process that's really critical, and that's where what I do differs from basic research. So it's not about necessarily finding out what a gene does, but figuring out how to make the best cells to treat a person with.
So heart attacks are one situation in which rebuilding blood vessels could have a significant impact. But, as Jo explains, it's not the only one.
So the other classic place that we see ischemic injury, which is effectively what a heart attack is, it also happens in, for example, in your leg, and it can be because you have diabetes and the circulation in your leg is compromised by the diabetes, and that can lead to amputation, for example. And this disease is called peripheral limb ischemia or critical limb ischemia, and that's one of the diseases that would be aiming to treat with this kind of new therapy.
Why does diabetes result in you having to amputate your limb?
One of the reasons that we believe is that the cells in the body that make the vasculature naturally to make the blood vessels become disorganized and are not able to rebuild that tissue themselves. So you lose that circulation in the lower limb most commonly. So the tissue can't repair itself. So what we're aiming to do is to take fresh, healthy, young cells and put them into that tissue so that they will operate where the native ones won't.
Is there a problem regarding rejection? Is there a fundamental problem using cells that aren't one's own?
So there's two different types of pluripotent stem cells. The first ones are embryonic stem cells, and in that case we can't choose what tissue type we get, and in that case you'd have to match as well as you can. And the major thing that we match for actually is not tissue matching but blood group matching, and that's the same as you would do for a kidney transplant or a liver transplant at the moment. And we could use immunosuppression drugs with the transplant to give them a better chance to take. The other source is called induced pluripotent stem cells, and they're effectively the same kind of cells, but we make them in the lab. And we can make them from skin, we can make them from blood, using a genetic trick that reprograms them into being a stem cell. We can then grow them in the same way that we do the embryonic pluripotent cells. And they have exactly the same capacity to differentiate or to mature into the different tissues. With those, you can choose the donor. So you could choose whichever tissue type you wanted, and what we're actually doing is looking at building banks of induced pluripotent stem cells with the most common tissue types for each country, so that they would then be the most useful clinical sources of cells for many different types of tissue.
So how far away is this treatment from the clinic? Well, it's still in research stages, and with success in animal models for the limb application, the team are now looking into creating models for the heart attack case. Whilst it may still be a few years away, Jo is hopeful that being able to rebuild blood vessels in patients could have a real impact on people's lives.
So at the moment, people die of heart attacks because the muscle function of the heart is compromised sufficiently that it can't pump anymore. Or they have long-term disability because their heart muscle doesn't function. If you can rebuild that muscle partly by rebuilding the blood vessels, or if you can save the tissue in the leg by restoring the blood supply, you don't lose that organ function. So your heart function is better, so your quality of life is better. In peripheral limb ischemia, you, for example, wouldn't lose the tissue from your leg, so you wouldn't end up having to have it amputated. Potentially, and that's the goal that we're working towards, is a single treatment for a long-term efficacy.
That was Jo Mountford there from the Scottish National Blood Transfusion Service.